Okay, I would like to also thank the organizer for having me here. And I think I slightly typed the title slightly differently, but it's actually the same talk. So don't worry. Sorry for any inconvenience caused. Um, so the idea is quite simple. We have heard just now from Wenwei about thermalization. And there has been a lot of studies on trying to understand how thermalization emerges in isolated systems. And then the question that I try to address here is how thermalization, how non-equilibrium states can be generated also within isolated systems, and whether we can see steady currents, at least for very long times. Okay, so before starting, of course, I would like to thank people who did a lot of these calculations, and actually some of the main ideas came from Xu Xiansong, my former PhD student. And so I would like to thank Xiansong and Guo Chu. And now I continue. So the outline is going to be this. First, I'll try to give an overview about ETH and prethermalization and also typicality. And then I will talk about the typicality of steady state currents and then give my conclusions. So let's say we take an isolated quantum system and we let it evolve. The question is similar to what was asked in the previous talk as well. Does it thermalize and in what sense? So can we describe after a long time the system with just a few parameters which are independent of the details of preparation of our initial state? Okay. And there has been a large number of reviews in this topic in the last 10 years or so. And here is a list, which I hope is relatively complete. And then the question can also be phrased in this way. For an isolated quantum system, I can always write my wave function as a superposition of eigenstates, and then the evolution will give still a wave function that can easily be written in this way. But we also know that in systems that thermalize, the long time dynamics, the state that you can see at long times can be very well represented by, for example, a microcanonical distribution or a canonical distribution. And how you actually get from these to this is not trivial. And there's been a lot of investigations. One way to approach this was initiated by von Neumann in 1929. And the idea was not to focus solely on the state, but actually look at local observables and see how they behave. And actually, you can see in systems that thermalize two different flavors of thermalizations. One is so-called strong thermalization, in which the expectation value of this local observed quantity approaches what is expected from my microcanonical ensemble for almost all time, which is represented in this plot here. Or people also talk about weak thermalization. In this case, the expectation value approaches the microcanonical one only after having performed a time average, which is this case here. Now, a lot of insights have come into this thanks to works by Sronidiki and by Deutsch in the early 90s, and in particular this idea that is known as the eigenstate thermalization hypothesis. In this case, the idea was if I need my system to represent what I expect from a canonical distribution, for example, then what my operators, local operators, should look like. And it turns out that if they look like this, then you will see emergence of statistical behavior. And these operators in the energy eigenbase have these two properties. The diagonal elements follow a smooth continuous function of the energy. And then the off-diagonal elements have a function of the two different energies. E is the average and omega is the difference of the energies. And Rij is a number drawn from a normal distribution. And this term takes care of normalization effects. And okay, so this was the idea of the eigenstate thermalization. And if it turns out that, as we can see here, that it works in many systems, non-integrable models. For example, here this is taken from the review by D'Alessio and Rigol, etc. If I take an integral model and I break integrability more and more, And now I look at the diagonal elements of some observable in the energy basis. I see that as I increase the system size, 18 to 21 to 24, and I'm in a strong, large, more non-integrable regime, you see that the values of the diagonals tend to collapse over a straight line. I'm not sure if you can see it from this side. If you don't see, I'm sure you know this paper. So. Okay. So, and the same happens for all other local observables. Actually, the integrable case is quite interesting. It's been studied recently very much by Rigol and others. And if they are interacting, there is a similar behavior also for integrable interacting models, where though these numbers are not drawn from a normal distribution, but from log normal one. Okay, so this is a very interesting approach, and it seems to be working in many nice cases. But there is also another point of view, which is so-called that of typicality. And there have been many works, and I just mentioned two here, by Goldstein and others, and Popescu and others, but also Tasaki, Gember, Mahler have done nice works in this direction. And yeah, basically, let's say you take a state, a pure state on a very large system, which has a constraint, and then you trace out a large portion of it, and you look at a small part, and then you will see that this is indistinguishable from, for example, a microcanonical distribution that you have prepared with the same constraint. And so you can see that you may not even need to start from canonical distribution, microcanonical, because if you choose even pure states, when you look only a portion of them, they are indistinguishable from this distribution. And all of these works were nice and interesting, but they're concentrated on equilibration and thermalization. And what we're trying to do is to go towards non-equilibrium steady state. To do this, though, we also have to think about dynamical typicality. And there was nice results by Barch and Gamer in 2009 and others that followed afterwards. And they show that even if you prepare two states which have a local observable, it's a very similar value at initial time, also at later times, the value will be quite similar. But as you go towards thermalization, the path could be a little bit different, and depending on the properties of the system. In particular, if the system has some weakly broken conserved quantities, the path to a thermalization may go to an intermediate stage, which is called prethermalization. And in this prethermalization regime period, the system thermalizes almost as if the conserved quantities are still there, and then only later, starts to deviate from it and really relax to the true equilibrium state. This is something that I had to mention because it will be quite important later on. Now, we have talked about thermalization, and we try to see whether we can go beyond towards non-equilibrium. So the idea is this. If I take, we're familiar with steady states when we have one bath and another bath, maybe a system in the middle, and along times we see a steady current. Now, what if everything is a large system and the evolution is purely unitary? Do we still see steady states? And for how long? Can the current be described just by a single number and not a distribution? And can we use ideas from ETH or typicality to answer these questions? So this is the model that we are considering. I take a spin chain with a certain number of spins on the left, a certain number of spins on the right, and a coupling between them. Most of the work, the coupling I consider would be very weak, but also we show what happens when the coupling would be larger later on. Such a approach has been used in many works, and here I mentioned just a few of them, where the system was preparing a particular initial state and then let it evolve and see what happens. But here we want to figure out whether the steady currents that you obtain for long times are typical, whether they are not dependent on the exact preparation of your initial state.
To do so, we use this Hamiltonian, which we know mixes very well. We chose this one that we've used in other papers where we study out of time order correlators, and we know that for these parameters, the level spacing statistic ratio is about is very close to 0.6, which is what we expect from GUE. Okay, so the two systems that we take are the same Hamiltonian, but what we do, we will prepare in different initial conditions, and then we see what happens. The coupling will be weak most of the time, and we put a coupling on this form, and overall there is no conserved quantity in this system except for energy. Okay, so now we take we prepare the left buff with states which are between a certain energy region here, and the right side on the other side here. And so basically the only difference is the energy difference between them. But we prepare them in 3 different ways, and we compare them. First way is we take just an eigenstate inside this energy region, and an eigenstate inside here, and we just let it evolve. Okay, this is what we will call a psi I. Then we also consider superpositions of eigenstates within this region and superposition of eigenstates within this region. So this will be our typical initial state. And of course, we will compare it to a microcanonical preparation, where in each region we take an evenly weighted mixture of all the eigenstates in that portion. Okay, and we try to analyze the current, the emergence, once we do this. For current, we look at the energy in one of the buff and see how it changes. And of course, we will compare also what happens on the right side, but here we'll just show you this. And how do we evaluate this? Okay, we evaluate in 2 different ways. One way is purely brute force. We just numerically evolve 28 spins, 14 for one side, 14 for the others, and let it evolve numerically and see what happens. And the other, we use a perturbative approach. We expect interesting things to happen when the coupling between the 2 chains is small. And there we use a perturbative approach. It's very similar to derivation of master equations, where we have correlations on the 2 different buffs and so on and so forth. Okay, so what do we observe? Here I show the current versus time, and we see 6 different curves. The lines are from exact simulations, brute force simulations, and the symbols are from the perturbative approach. And we see that for these values of coupling between the system and the buff, which is 0.01, it works really well. So perturbative approach we can trust. Then we see 3 different behaviors. The black and lines with circles, it corresponds to what we obtain if we prepare the states in microcanonical initial conditions. And we see that after a transient, it goes to a very flat behavior, a steady behavior. The red with triangles is from preparing a single eigenstate in one of the 2 sides. And we see also, in this case, after a transient, it goes to a very flat behavior with a bit more oscillation than the microcanonical one, slightly away from it. Okay, but this is just one realization for a system of 12 plus 12. And also, this is the blue with squares is just one typical realization of fairly small system, only 12 by 12, 12 plus 12. And we see also after a transient, it stays close to the microcanonical one, but it oscillates more. And this is kind of expected because we have coherences within the initial preparations. Then you can say, okay, but what happens if I prepare many of them? So I prepare about 400 of them, and I look at this, oops, sorry. And I look at the distribution of the possible currents that I obtain, and I will see that this distribution is picked at the value predicted from the microcanonical ensemble, both if I use the eigenstates, which is the red histograms, or the typical one, which is the blue histograms. And in particular, if I look at the expectation value so the average over many different realization of typical states, I see they coincides exactly with the one expected from microcanonical ensemble. And for this, we actually have an analytical result. It's not just a numerical evidence. Okay. So we see that many different realizations are distributed around the expectation value from the microcanonical ensemble. But what happens to this variance, this distribution? Okay. So we plot the standard deviation of this distribution versus system size. Here up to 28 spins, so up to 14 plus 14. And we see that the standard deviation decreases, okay? So we can, maybe with some good luck, hope that it goes to the what expectation value from the macrocanonical ensemble. We'll get more precise on this later on. Okay, another thing that we can try to do is to increase the distance between the energies of how I prepare the system. And so if I do this and increase the energy distance between them, I also see that the current increases linearly. And so whatever I'm testing is still within the linear response region. What I can also observe is that if I increase the system size, the fluctuations around this linear response, okay, becomes smaller and smaller. You see, for 22, we have a bit of fluctuations. But as I go to 30, it's quite a very nice, smooth straight line. We can also compare the results with prediction from ETH. I take the ETH ansatz. I estimate the value of the expectation value on the diagonals and of the diagonals from small system size and make a smooth curve for larger system size, and then throw it in my perturbative expression and look at the current, and I see that it matches the results from ETH match the other results. So all of these results are consistent with what we'd expect from ETH. Now you can say, okay, but what happens if first of all, this is still a unitary system, so this steady current cannot go on forever. Eventually, we'll have to thermalize, the current will have to be 0. So what happens at long times? And indeed, we look both at long times, but also for different values of the coupling. And we see that eventually the current goes down. And also, if the coupling is strong, we don't see a clear plateau close to the expectation from microcanonical ensemble, which is this dash dot line. But we see maybe some small plateaus here, but it's not a clear emergence of quasi-steady state currents. Okay, but one important point though is that for these very large systems, even if the coupling is large, if the system becomes larger and larger, the coupling is only in one place. So it eventually will always become a perturbative effect. So we can try to use perturbation theory, and we see that actually the long time dynamics is expected to go as to collapse if I rescale the time as a gamma square over n. And in fact, we see that if you do so, all the curves match on top of this one. So now this curve looks a little bit weird because we wanted to show clearly the short times and also the long times. So for short times, we have a linear line, and then for longer after one, we have a log. So it's a very weird way of presenting this, but this will help us to show both behaviors. And we see that there is a clear collapse at long times, which is actually what we expect from prethermalization. So in short, there are 3 regimes which can be seen clearly for weak coupling. First regime is a transient, then let's say quasi-steady current, because it will last only for a time that goes as n over gamma square, and then a relaxation to 0 current. And the idea is that this intermediate regime is really related to prethermalization, where here the weakly broken conserved quantity is the energy of each of the 2 buffs. Okay, this is quite nice, but there are 3 fundamental flaws still. Number 1, I've shown you the distribution of the currents, but I didn't show clearly how this changes as a system size, because we're limited to only 28 spins in total in that work. And we also couldn't tell whether this is weak weak prethermalization or strong prethermalization? Do we need to take an average, or it will be true without even taking an average for any time? And it's also very difficult to test this experimentally. All these states we prepare were based on eigenstates of a complex many-body system. And this is really, really demanding to do experimentally. So how can we address all of these problems? And the way to address all of these three problems is by using different initial preparations. Here we use an initial condition which is drawn from the mean energy ensemble, and which is basically states which have an expectation value of the energies which is very close to a given number. And we chose particular initial preparations which are actually local tensor products, and locally we have a superposition of up and down. And what you have to do simply is to find the u and the v such that your state is in there. And you can run simple optimization problems, gradient descent and so on, that to give you the correct values for u and v. Okay, and these are great advantages, both numerically and experimentally. Experimentally, you can definitely do this, it's very easy. Numerical also, it allows us to study much larger system because we don't have to start from eigenstates. And just to give you an idea of this initial preparation, instead of having a single eigenstate or a equal mixture of states within a band or a superposition of states within a band, we have a state which has overlap with a large number of states across the spectrum. So it seems a lot harder, a lot worse. But here is what we see. Let's say I take 20, 28, 24 or 28 spins in total. And then I plot the largest possible current or the smallest possible current. We see as we increase the system size, this band of between large and smallest possible currents decreases significantly. But we can be a little bit more precise on that. We can look at the distribution of currents and look at the variance. And now, because I can prepare much easier initial condition, I can study up to 52 spins in perturbation, 26 plus 26. And in doing so, I can see a very clear exponential decay of the current at a given time. So clearly the distribution is going down, the variance of distribution is going down exponentially towards what? Towards actually what we expect from the microcanonical ensemble. Here I show the distributions for different system sizes. You see with 52 is basically a very clear peak. So at a given time, it doesn't matter how I prepare the state, I will see always the same current, okay? If the system is large enough, with very, very precisely. But this is a given time. What happens over time? I could have maybe fluctuations. So now we study this. I take a single preparation of the system. And I evolve it over time for 36 or for 52 spins. For 36, the triangles, you see that there is wide oscillations, while for 52, it's very flat. And here the scale is actually quite small. So now if I look at the variance of the current of a single realization over a period of time, I see this variance also over time goes down exponentially. So I really have a very clear value of the steady current. And so in this way, using this initial condition, which is a product state taken from the mean energy ensemble, we can address all the three big problems that were left over from the first half of the talk. There is a clear exponential decrease of the variance with the system size. We observe a strong prethermalization because we don't need to take time average over here. Just a single realization, just follow it. It will be close to the microcanonical, what I expect from microcanonical preparations. And this can be easily tested experimentally. So now people can go to the lab and do it. Okay. So then I can conclude. We see the steady currents are typical. They last for a time that is proportional to the system size, at least. They are related to prethermalization. And now we have initial conditions that can be tested in experiments. And of course, there are other things that we can look at. For example, if you have integrable models instead, if how local the Hamiltonians can be, whether this helps or not. And with this, I would like to thank you and thank my collaborators on all the topics of quantum chaos and relaxation that have helped me throughout these years, and in particular, Xiansong and Guochu. Okay, thanks.
Yeah, and you have time for questions, so maybe let's start here. Let's wait for the microphone. Yeah.
Yeah, thank you. I think if I didn't miss something, you always consider local interaction between the two subsystems. Is it correct? You have two systems and you have local interaction between the systems. Is
Yes,
that
it's
correct?
just in one place at the
Okay.
yes.
Do you have feelings what would happen if you would consider long range interactions? How things would change?
Yeah, I think so. So as I mentioned before, it has a lot to do with the fact that as you increase the system size, this becomes always a perturbative effect. So now if you have a long range interactions, this may not apply anymore. And so it may be harder. Okay? I think you need a nice, clear, short boundary and skin effects.
So you might have problem in having a well-defined limit, do you think, or?
Yeah, or maybe it could work, but we need a clearly smaller coupling strength.
Hi, thank you for a nice talk. I was wondering about the current. I didn't quite understand the definition. Is that the change in energy per time or like energy transfer? Because your system is isolated, right? So I wonder where does the current go? And also you said microcanonical state has a current, but microcanonical state is how do you call that? Well, it doesn't evolve in time, right? So
Okay, so let me try to address.
yeah, okay.
It's the initial preparation is microcanonical for one half, microcanonical for another half at different energies. For example, this is the reference state. Okay, so in this case, you expect current between them for finite time, and eventually the current will go down to zero because at the end of the day, the system is isolated. So at very long times, the current will be zero. Now, the question that let's put it this way. I have something at a certain energy, something at another energy, I couple them, and they're huge, okay? Then you expect a steady current to last for a really long time. Now, the question is, how long is this time, and how carefully do I need to prepare them to see a particular current, okay? And the current goes just from the left to the right, and eventually it goes down to zero. So this is the initial preparation. I hope now it's clearer. Okay, and then as I shown what happens at long times, okay, at long times we do expect the current to go down to zero. The question is what happens intermediate times and how long these intermediate times are.
Oh, and there is an analytical formula for intermediate times.
Yes, we have a scaling at least at this timing. You should go at like n over gamma square. So the weaker the gamma, the coupling between the two buffs, and the larger the buffs, the longer this time is.
So it's always expected that the intermediately it's kind of constant, this current.
That's right.
Okay, thank you.
Thanks for an interesting talk, Dario. So I'm curious whether the time at which the current goes to zero coincides with something where the entanglement also reaches the maximum value.
Yeah. We haven't. So one of the things we would like to do more is to study exactly what is happening within the buffs and the correlation within the buffs. And it's in the plans, but we're not yet looked into that.
Thanks.
Yeah. So I cannot really answer. There are also boundary effects. So there are many things that are happening. There should be something related to also square root of n. So yeah, we need to investigate further.
Thanks.
Okay, unless there are no further questions, we would have to thank Dario again and move on to the next speaker. Thank you so much.